beginning of limits in calculus, right? I actually launched into the topic by talking about gradient and the whole idea of rise over run and what it looks like when you've got rise over run on an increasingly small scale. And that's why we had to talk about limits and h approaching 0, blah, 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 right? What I left out was some of the building blocks that go underneath all of that calculus, that formal understanding. The reason why I left them out is because I wanted you to get the concept and motivate you for why are we learning this topic at all, rather than let you get bogged down in some. Really, these ideas are kind of weird. You might think, why are we looking at this anyway? We're not getting tested on it. In fact, it even says in bold, it says not to be examined. Okay, so why are we learning it? Well, first reason, these are legitimately important. Okay, they make sense of a lot of the stuff that we've actually already been assuming. Okay, and secondly, even though these aren't accessible in a direct way, okay, and as I show you the concepts, you'll be like, oh, I see that you can't really write a question that tests whether you understand this or not. This will become really, really important when we look at max-min, which is a big topic under calculus later on. Okay. So, I have two concepts, right? So let's launch into it. The first one is called continuity. Continuity. Simple idea. I'm going to give you a simple, intuitive definition for this first, and then I'll give you sort of a more technical, rigorous one. Okay? So we're talking about functions and graphs. To say something is continuous, this is my intuitive definition. To say something is continuous, I guess I would ask, does the graph, does it have any breaks in it? Like, does it ever stop and then start again? Okay? Some of you may have heard, and this is a good way to put it. Can you draw it, the graph, I mean, without lifting your pen or pencil? Okay, now. So, okay, now, like I said, this is a basic idea. You can think of some graphs that work with this and some which violate this idea. Okay, so clear example, easy example. Something like, say, y equals 1 over x. Right? This is hyperbola. So what's it look like? Well, you've got one branch of it which is totally separate, therefore not continuous, with the other. Okay? So we would say that this graph is continuous for two separate domains. Okay? We'd say it's continuous for x is less than 0 and x is greater than 0. Well, actually I should say 4. Okay? So it's continuous in certain places. It's not like there's breaks everywhere, okay, and as you zoom in it's all tattered and broken. This part is continuous, and so is this part, but there's that discontinuity at x equals 0. Okay? So that's the basic idea, but let's get a more technical, rigorous definition. It's got 3 parts to it, this technical definition. Okay? So number 1, we want the function, like this, to be defined at a particular point. Function is defined. Now, let's just give an example point, like say x equals c, where c is just any old constant that you like, okay, a real number, right? And you can pick it anywhere along the graph. So, is the function defined at, for instance, x equals 1 on this graph? Well, yes it is. So that's why this graph is continuous for that point. And I can pick a whole bunch of other ones. The only one I can't pick it for is x equals 0. Okay, so there's the first part. Now, the second part starts to get a little weird, and I'm going to give you some counter examples to help you try and understand this. Okay, let me give you the technical part first. The limit namely as x approaches c of f of x exists, and I'm about to give you some weird words which I need to explain a little bit, so I'm just going to put it down first, and is the same from above or below, or and below. What does this mean? Okay, so you think about a function. Let's go with something like, say, no, which one should I pick? Oh yeah, no, I'll just do this. actually I should call this f of x. When you think about this function, because it's continuous everywhere, right? If I take a limit at any point, it wouldn't be that hard to work out. For instance, the limit as x approaches 0, right, of f of x. In this case, because there's no breaks, all I have to do is put in x equals 0, right? And you get 0. That's what I'm approaching towards 0. Okay? However, think about this graph up here. Okay? Even though the graph doesn't exist at x equals 0, I can think about the limit as x approaches 0 of 1 on x. Okay? I can think about the limit even if I can't exist there. Okay? But then you come up with a problem. Because what would you say the limit is equal to? What are you approaching as x gets closer and closer to 0? Now, there's two answers. What are the two answers? Okay, if I have a look at this side, right? In other words, if I come from the right, or if I come from the larger values, that would be above. Okay. If you come from above, you're getting larger and larger and larger and larger. So you would say it's approaching infinity. Okay. But if you come from the opposite side, you get a completely different story, right? It's like they're totally unrelated. Okay. So you would say minus infinity. Okay. So how can we distinguish between these? What we say is, I have to introduce some notation to say, there's a limit, but which way are you coming from? Okay, are you coming from above, from positive values, values above it, or below, from values that are less than it? Okay, so another way of saying this is, limit as x approaches c, and then to indicate that I'm coming from a particular direction, I'll put a sign above the value I'm approaching. Okay, so what would this mean? This means I'm approaching c from above, from the positive side. This is positive, that's negative, right? So this is sort of like, if you like, from right to left. Or, as I've said here, from above. Now I want the limit as I approach this value you see from one side, I want it to be equal to the value from the other side. I want them to be the same. Okay? And as you can see, like in this example, they're not always the same. So just to fill this out, okay, if I was coming from above, I would get infinity. Okay? And if I go from below, okay, it looks a bit weird because they're like 0 positive and 0 negative. The negative and the positive indicate a direction. Okay? Of 1 over x, that's equal to negative infinity. Okay? So one of the reasons why this function is not continuous is not only that the function isn't defined. Okay, I could define the function somewhere. I could say, you know, let's just let it equal there. Okay, at x equals 0, it goes to the origin. Okay, but it wouldn't obey the rules of this limit. Okay, you take the limit from one way, you get one thing. You take it from the other way, you get a different thing. Okay, so even if it were defined, even if I could tick off for A, I can't tick off for B. It doesn't approach the same thing. So this is, I'll just fill this out, this is left to right, or to say it another way, from below. Okay, lastly, what's the third bit? And it's kind of superfluous, it's kind of necessary, but it's there in the textbook definition, so I'm going to give it to you anyway. Number one, the function is defined. Number two, there's a limit, and coming from both directions, it's the same. And the third part is, the function is defined, or sorry, I should say f of c, that's a better way to say it, equals the limit above that I'm talking about. Okay? So for instance, I mean, it'd be a bit weird, but you know, you can imagine a possibility for a situation. If I gave you this function, so this is a piecewise function, okay? So this would be f of x is equal to what? How would I define it? I'd say it's x squared for x is less than 0. Let's make it 1 for x equals 0. And it goes back to being x squared for x is greater than 0. It's a weird function, but let's just go with it anyway. Okay? So it's sort of coming down, the limit's approaching, everything's fine, and then it goes whoop at that one value. And then as you keep going, it just keeps on marching on its merry way. Okay? So here, f of c, right? Actually, I should go from the top. The function is defined at that point that I'm interested in. The limit exists, and from both sides it's the same. But the thing that it's defined as isn't the same as the limit. So you'd say, this thing is not continuous. It's got a hole in it. Okay? Again, I can't draw it without lifting my pen, pencil, marker, whatever. Okay? So, these are the three parts of continuity. Like I said, this is important later on when we get to max-min, because when you have functions that aren't continuous, that leads to a problem for when you're trying to find the maximum value of a function or the minimum value. Okay? So take this idea of continuity and file it, stuff it away in the back of your mind, and we'll come back to it in a few weeks. Okay? So this is continuity.